Okay, what we're going to be taking a look at today is going to be some more work with rates of change and tangent lines. Now when we discussed our section 2.1, okay, we did some work already on dealing with rates of change and also with tangent lines. We had talked about finding the average velocity in a problem where we drop a rock, if you will, from the cliff. And we discussed, we looked at a picture about how we could find the instantaneous speed and what that meant graphically. And ultimately, remember what it boiled down to is that, you know, if we can find 2 points on a line, we can connect them for certain, and we can find the slope because we have a slope formula. But ultimately, how do we find the slope at 1 point on a given curve? And that involved using some limits and finding the slope of what we call the tangent line, which is going to be the line that touches the curve at just 1 point instead of 2. Okay? So, in review, our picture like that looked if we had some curve and we connected it with 2 points, or that connection between the 2 points, that line is called a secant line. Okay. So, and again, we could draw it as a line or a segment, whatever, but either way, that's a secant line. And if we have a line that just touches at 1 point, then we call that a tangent line. So this one is the secant line, this one would be the tangent line. Alright, and so our job at this point is to decide how do we go about finding the slope of a curve at a point. In other words, how do we find the slope of the tangent line to any given curve at any point. Okay? And we already have some pretty good insight because we've already done it when we did our section 2.1. So our work today is going to be very similar to that. Okay? And so before we get to that, though, we're going to talk about first, before we talk about instantaneous change again, let's review what we know about average rate of change. And in the case of the previous problem when we dealt with rates and distances and times and so on, remember that our average speed, or our average velocity, is the change in distance over the change in time, which ultimately is a slope, because if we were to draw a graph of this, our slope calculation with the 2 points that we had on whatever curve we dealt with would be a change in some distance over a change in some time, and that would give us, and think of that why that's true. The units on this, the distance units would be something like miles or meters or yards, and our time units would be seconds, minutes, hours, whatever the case may be. So this fraction that we get when we do that calculation gives us a rate. Okay? Now, one of the things that we're going to be asked to do today is find the average rate of change for, let's just say, for a particular function like ln x. Okay? So if I have the function ln x, and what I want to do is I want to find the average rate of change over the interval 1 to 4. So if I want to find the average rate of change for this function over the interval 1 to 4. So algebra-wise, we're definitely going to be able to do some algebra that we'll be able to get an answer here. But before we do the algebra part, let's think about what are we really being asked here. Well, we know that natural log at 1 is 0, and from there it goes up as such. We know that before 1 it goes down, it has an asymptote at y equal x equals 0. And so with that said, if we do 1, 0, that point is the point that we're interested in on the left end point of this interval. Fair enough? Okay. And if we go out to 4, okay, we can see that it's going to be 4 something. It's going to be actually 4 ln 4 would be the coordinates of the point on the right end point of this interval. Okay, now what we're after here in terms of an average rate of change, okay, is the slope between these 2 points. That's what an average rate of change is. It's the change in y over the change in x. So when we dealt with distance and time, we said the change in distance over the change in time. Okay, in general, the average rate of change is the change in y over the change in x. Okay? So this is our average rate of change. Which again, algebraically, we can do algebra to figure out what this is. Okay, geometrically, it's essentially the slope of what kind of line that connects these two? It's the slope of the secant line. Right? That's all we're calculating here when we want the average rate of change. So with that said, let's go ahead and calculate it with our algebra now. If we look at the points in question here, if we want to find the slope between those 2 points, we go ln4 minus 0 on top, and then 4 minus 1 on the bottom, and so ultimately we have ln4 over 3. And that right there would be the average rate of change. Okay? Now just for comparison's sake, go ahead and give me a decimal for that, just so we know about how steep that is. 0.462. Alright, so not terribly steep, as we'd imagine. I mean, the natural log function's a fairly slow growing function once we get past 1. Okay, and then just for comparison's sake, let's look at a different interval, like say for instance, if we wanted to take that same function on the interval, let's say 50 to 53. We'll keep it the same length. Okay, so we're going to go from 50 to 53. Now, let's make a conjecture before we find the answer to this. Okay, as we go out to the right, what does this natural log function do? It continues to grow, but it should continue to grow at what kind of rate? Essentially a slower rate. So what should we expect the slope to be like between the 2 points when we're out at 50 to 53? Should be smaller than 0.462, shouldn't it? Based on the growth of that function. Okay. So let's check it out and see if that's the case. So our points then would be 50 ln 50 and 53 ln 53. So if we're going to calculate this average rate of change, what's step 1 in any problem like this? Figure out what? Figure out the 2 points. You know what the 2 points are. You can't calculate the slopes unless you know the 2 points. So if we do that, ln 53 minus ln 50 on top, 50 minus 3 on the bottom is 3. So I'll go ahead and punch that in, and what do we get for an answer? Approximately what? What is it? Alright, so it's 194, then it's just 19. And again, 3 decimal places always when we round. And with that said, does it match up with what we thought? Yeah. Notice that it's still growing, of course. It still has a positive slope here. Okay? And it never wouldn't, no matter how big of numbers we pick. But as we go further to the right, okay, we're going to get a little bit less of a slope each time we go further and further right. Alright, so, like I said, with that, we've essentially relearned how to make sure we can calculate the average rate of change for a given function. Okay. All right. Now, I want to discuss. I want to rediscuss essentially, if we were to take that same function and a minute ago we did 0 to 4. Let's just say it looked like that. Okay. And I'm gonna not a very straight line, but get the idea. So if I'm going to connect those two, that secant line right there, okay, is going to be the average rate of change. Now, here's my question that I want to ask, and we've already discussed this, so we probably already know the answer, but we'll talk about it again. If I wanted to say use this secant line to estimate the slope at 1, 0, okay, how good of a job is that secant line going to do to estimate the actual slope at that point? And again, I'm going to draw the secant line extended here a little bit. Okay. If I take the slope of this secant line right here, which I know is 0.462, does that tell me the story about what's going on at 1 very well? Well, it does in a sense because it's positive, number 1. So it is positive, so it's not terribly unreasonable, I guess, right? But ultimately, what should we expect that the real answer is for the slope at 1 itself compared to 0.462? Should be steeper than that, shouldn't it? Did you say? Yeah, it should be steeper than that. So, question is, how do we get, if this is not a very good approximation to the slope at that point, how could we get a better approximation then? Okay. Again, I want the slope at 1. So what, instead of using 4 ln4, what might be a better point to use to get a better approximation to what's going on at 1? Okay, how about using 2 ln2, something closer? Wouldn't I get a better approximation? Think about what the picture would look like. If I connected those 2 points, right, now what does it look like in terms of the secant line? The secant line slope, it looks like it's bigger than the other one, doesn't it? Which ultimately would be closer to what we're after, true? And so if 2 ln2 gives us a better approximation, then, right, let's use that instead. But what would be better than 2 ln2? About 1.5 ln 1.5. Okay, and ultimately, if we let these numbers get closer, okay, we can calculate, if we just kept, if we did 4 or 5 of these, we could get closer and closer. We could calculate the slopes as we get closer to 1, true? And ultimately, as we get closer to 1, those slopes are going to get closer to the true slope at 1. Agreed? So looking at the calculator, if you will, if we take our function that we're dealing with, natural log of x, and we graph it, get, of course, the picture that we assumed. And now what I want to do here next is I'm going to zoom in on that point that we're interested in. This 1, 0 point, thereabouts. And if I keep zooming in on this point, I want you to notice 2 things about what happens here. If we keep zooming in around 1, what seems to be happening in our screen? Okay. It's essentially becoming linear, isn't it? Okay, because really when I zoom in that far, what am I looking at in terms of that function? I'm looking at so small a part of it that it looks linear, doesn't it? Okay. So now what I'm going to do this time is I'm going to do the trace command at this point. And I'm going to pick a point that's very, very close to 1, 0. Okay. Let's just say that point. That's not 1, 0 right there, but it's pretty darn close. Right? So I'm going to write the coordinates down, 1.001496, and the y coordinate 0.00144949. Okay. And what I'm going to do is I'm going to take those 2 points and I'm going to calculate a slope, because ultimately that's pretty close. We obviously could get closer if we zoomed in more and so on, but for now, for our purposes, that should probably do it. So let's go ahead and calculate that slope. So I'm going to go this number, 0.004, excuse me, 1, that is, 14949 minus 0, which is just 0. And we're going to divide that by, and on the bottom, 1.001496 minus 1 on the bottom. Whoops, did I forget something? Forgot my look up times. Say that didn't look like the right answer. There we go. There, that looks better. Okay. So at this point, when we're that close to 1, okay, our slope appears to be 0.999, which is very, very close to what? 1. And if we got even closer, the number would be even closer to 1. So I'm going to tell you right now, the answer is 1. The slope at 1 is 1 in this particular case. Okay, but ultimately we can get an estimate by getting really close and close, keep getting closer and closer and closer, and we get an estimate for the actual slope at that line, or at that point, I should say. So, with that said, what we still have, though, by getting very, very close to it, is we still have an estimate, though. And we might conjecture that the answer is 1 here, okay, but is there a way that we can algebraically show that the answer is 1? Okay, that's the issue that we're going to look at next. Okay, can we show that the answer is, in fact, 1, instead of just taking an approximation for it? Question. Alright. So, as we set up last time, and we're still going to set it up the same way this time, okay, we can find the slope of a curve at a point, okay, by using that idea of using a point that is h away from it in the x direction. Okay, so let's go and review here. Let's say we have y equals, let's say 2x squared plus 2. Okay. We're not going to do it this time with the natural log function. We're going to come back to that one at some point later. But ultimately, if we have some polynomial, this process is the easiest to do with polynomials because it's just a matter of multiplying in order to get our right answer. But let's say I want to know what's the slope of 2x squared plus 2, and I want to know at x equals, let's say, 4. Okay? So I want to know the slope of that curve at that point. And again, I could do what I did in this problem, and I could estimate it. I could zoom in real close to 4, whatever. In this case, it would be, what, 434? Okay? So I could zoom in real close to that point, and I could get an approximate answer to what the slope might be. But the question is, can we calculate exactly what the slope would be for this curve at this point? And to do that, what we're going to do is we're going to take a point, whatever it is, in this case 434, and we're going to pick another point that is going to be h away from it. And so keeping in mind that the points in question here are 434, and then 4 plus h, and then the y value at 4 plus h. So remember, we got 4 because we plugged 4 into the formula. True? So how are we going to get the y value for 4 plus h? We're going to take 4 plus h and put it into the formula. So in practice, it's going to look like f of 4 plus h. That's going to be our y value. Okay? Now, I'm not going to see what that is in this particular case. I'm going to write it out in general first. But ultimately, the answer to this is still, these are still 2 points, okay, even though we don't know what h is. Okay, it's f of 4 plus h minus f of 4, okay, over 4 plus h minus 4. Now again, I'm just generalizing here. I already know what f of 4 is. It's 34. I'm going to put that in there in a minute. But in general, this is the setup that we're going to use for any function at any point. Okay. We're going to put 4 plus h in. We're going to put 4 in. Get an answer and subtract them. And then on the bottom, we're going to have 4 plus h minus 4. And what's always going to happen on the bottom here in a problem like this? The 4's will cancel, and I'm going to have h on the bottom. So before we actually do the calculation on that particular problem, okay, let's take a look at how we could generalize this even further. If I took any curve, and again, it doesn't matter what it looks like, say it looks like this, and I pick that point, and I pick that point, this point right here is going to have coordinates, okay, whatever I want to call it. Let's call it a, f of a. Okay. So I don't know what the x value is at that point. I don't know what the y value is at that point, but I know it has coordinates a, f of a. So a could be any x. F of a is going to be what we get when we put a into the function, and that gives us our y coordinate no matter what function, no matter where we are. So we're going to make a general statement here about how we're going to calculate this for any function at any point. Okay. So this point right here, remember if it's h away from the original point, then that point is going to have coordinates a plus h and f of a plus h. Okay. Questions so far? Alright, so with that said, even though there's no numbers here, I can still write down what is the slope that connects these 2 points. Well, it's f of a plus h minus f of a all over a plus h minus a, which simplifies to this, because a plus h minus a is always going to be what? H. Okay. Alright, so this formula that we've written here, which ultimately doesn't come out of the woodwork, it's because of the fact that we're just taking 2 arbitrary points on some arbitrary curve. Okay, this formula right here is going to give us the slope between any 2 points on any curve that are h away from each other. Fair enough? Okay. Now, here's the issue though. Okay, we really don't want the slope of a secant line here. We want the slope of a tangent line. We want the slope at a. Not between a and a plus h. We want the slope at a. So like we discussed before, what can we do to make it so that it's not the slope between these 2 points, that it's actually the slope at a? Okay, we let h become what? Let h become 0. Because if h were 0, then how much space would be between these 2 points? None. So in practice, we can't do that with our slope formula because we need 2 points. But we can do it with limits, because we can take the limit of this expression as h approaches 0. Right. And this right here is probably one of the 2 or 3 most important equations in calculus. Some might say in math in general. Okay? Because that equation right there is the key to us being able to find the equation of a curve at a certain point, at 1 point. Not between 2 points, but at 1 point. And this equation is going to give us our slope of any curve. So this gives us the slope of any curve at any point. Okay. That's why this is of high importance. Okay, that gives us the slope of any curve at any point. Okay. Now, in practice then, okay, how does that work? What are we going to do in practice to figure out the actual slope at this particular point? So let's go back up to our previous example, which was this one. We already have this set up. We know that if we want the slope of the tangent line though, okay, the slope of the tangent line, or the slope of the curve at the point, which are one and the same, okay, and I'll put that on here just so we have it in writing. So it gives the slope of any curve at any point, also the slope of the tangent line at point A. Okay. So those two things are one and the same. Alright, now we have a fairly good idea at this point what the algebra, what kind of algebra it's going to take. I know we've all seen the algebra that it's going to take. Okay. I know that we need a lot of practice on the algebra though, based on the quiz. Okay. So a couple of you got that problem right where you actually had to do this, but most of us not so much. So therefore, today we're going to be practicing more using that technique to figure out what is the slope of the tangent line, what is the slope of this curve at any point. So we already have set up our sentence here. Now to put it into practice, to actually find the answer to the question that we posed at the beginning, okay, we are going to figure out what is f of 4 plus h. Well, we know f of x is 2x squared plus 2. So if we want to take 4 plus h and plug it in for x, okay, that would give us an expression for f of 4 plus h. So in our case, it'd be 2 times 4 plus h squared plus 2. Okay. That right there is f of 4 plus h. It's our function with 4 plus h plugged into it. That's f of 4 plus h. Okay. And then we're going to subtract from that. And if you want to, go ahead and put parentheses around that. You can keep track of both parts separately. And our next part, we want f of 4. Well, what do we know about 4? Putting 4 in will give us what? 34. Okay. And on the bottom, we have h. And notice I didn't do anything with the limit yet. We'll bring that back in. I don't want to write it 10 times, so we'll just leave it alone for the time being. But keep in mind it's a limit problem, so when we get done, we're going to take the limit as h approaches 0. But with that said, we have it set up properly. Questions on any part of that, how I got what I got? So again, we're putting 4 plus h into that function. Okay. And once we do that, now we can just do the algebra that it takes to expand this. So if we do 2 times 4 plus h all squared is 16, that is. 16 plus 8h plus h squared plus 2. Still have that plus 2 out there, minus 34 out here still, all over h. So all we did in step 2 here is expand the 4 plus h. And then from there I would multiply the 2 into the parentheses in this case. So 32 plus 16h plus 2h squared. Okay, and notice that 2 has nothing to do with this 2 over here, so we still have a plus 2 here. Minus 34, of course. Alright, and as we simplify the inside, what do we notice about the number part? We have 32 and 2, which is 34, and why is that good? It's going to cancel the negative 34, which is good. On the top, we need to have all the constants gone. So if all the constants aren't gone, then something's not right. Let's go back and see if you did the algebra wrong somewhere. So with that said, we're going to wind up with 16h plus 2h squared all over h, because the constants will all be gone. And once we do that, then we can factor an h out of the top. All right, h and then 16 plus 2h all over h, which that is good because keep in mind we couldn't do this limit at first because there was a 0 on the bottom if we had an h down there. But now we don't have an h down there and we're left with 16 plus 2h. So now the sentence reads the limit as h approaches 0 of 16 plus 2h. And with that said, right, we can now directly evaluate the limit, and what's our final answer then? 16. And again, what is 16? It's the slope of the curve at the point x equals 4, and what curve? The curve 2x squared plus 2. So this is the slope. This is the slope of a specific function at a specific point. True? Okay. It's also, if we were to draw a tangent line on the graph, it would be the slope of the tangent line, because again, the tangent line and the curve are equal. So they have the same slope. Now, questions so far on the algebra part?
Like rather than going through all those steps on the test or quiz or something, wouldn't we just be able to know that the equation is always going to be the constant like x plus h, and then minus f of x over h, with the variable on the outside of the first.
So, I mean, ultimately, what are you trying to do? You're trying to get to 16 some other way? I mean,
Isn't the equation going to be formed the same way every time?
well, I mean, keep in mind that when we put f into our function, it's totally going to depend on what the function is. We use 2x squared in this case. Does it always have to be 2x squared that we're working with? No, it could be a completely different function. No, it could be cosine x. And that's going to be cosine x plus h minus cosine x You will? So the algebra could be different. I mean, with the polynomial, the algebra is very similar. We're going to do some expansion and combining like terms, and hopefully the h's will drop out, and we'll be able to plug in 0 and get an answer. Okay? But depending on what the function is, but really each individual function is going to have its own answer here, depending on what function it is and what point we're at. Because even think about right now, what if I asked you to do the same problem, the same equation, I asked you to do it at 5 instead of 4? Okay? Would you be able to just look at this and say, oh, it's 25? No. Okay? You'd have to go through the same process again, but instead of using a 4 here, we'd have to use what? We'd have to use a 5. So if I asked you to find this answer, find the slope of this curve at 10 different points, you'd ultimately have 10 different problems to do, wouldn't you? Anybody think of a way we could do it with where we wouldn't have to do 10 different problems? I think a way we could do this where we just would have to do it once and then be able to come up with an answer for any of the points in the whole line. I mean, ultimately we did this work when the a, if you will, in my equation, we did this when the a was specifically 4, right? So this is only good for 4. Okay. Would there be a way to do it so that it was good for any point? Yeah. What if we just left it as a? If we just left it as a and we did the work here, could we maybe come up with a formula that involves a where we could just plug in an x and then just do that for every one? Let's try it, see if it works. Because if it works, that would be pretty great, because then we'd only have to do that work one time and then it would be good for any point. Right? So let's see if it works. So again, my function is 2x squared plus 2. And if I go to fill in my blanks in the formula, the limit as h approaches 0, f of a plus h minus f of a all over h. Okay, let's see what happens when we don't put a number in for a. So if we put a plus h into our formula, it's going to look like 2a plus h squared plus 2. Right? Again, that is f of a plus h. That's our function evaluated at a plus h. Okay? We're taking the a plus h and we're plugging it into our function for that first part on the top. The second part, we're plugging an a in there, so it would simply be 2a squared plus 2. And make sure you put that in parentheses. Okay? If you wrote this the same way I just wrote it, when there was no parentheses around it, it would not be right. Because keep in mind that negative 2a squared plus 2 and negative in parentheses 2a squared plus 2, those are not the same, are they? Okay. I can tell you right now, first quiz, first test, mark it wrong all the time because people don't put that in parentheses. Okay, that 2 is not positive anymore, it's what? It's negative. If you put it in there like that, that's completely wrong. True? It's also going to give you fifths because you're not going to get stuff to drop out like you need to if you don't do it either. So with that said, that's the top of our equation, okay, with just a general a in there instead of a number. Okay? On the bottom, it's still what? Still h. Okay? Still going to do the math the same way. We're still going to expand first, and then hopefully we can combine some like terms. We'll see what happens here. So if I do a squared plus 2ah plus h squared plus 2, again, that's my top part, 2a squared plus 2 all over h. So that would be my step 2. It'd just be expanding the a plus h. Again, if you can't expand that in your head, then write it down twice and start FOILing. A plus h times a plus h, a squared, ah, h squared. Make sure you can get that. Like I said, at this point, you may be able to do that in your head. If you can't, write it down and FOIL it. You can't. So distribute 2a squared plus 4ah plus 2h squared plus 2 minus 2a squared plus 2. So we distributed. And then from there, we'll combine any like terms. In this particular case, there's no like terms in there in the first parentheses. We already know there's no like terms in that parentheses. So at this point, let's subtract. So if we subtract these two from the stuff we have over here, okay, what's going to happen? What do we got? We got a 2a squared right here, and we got a 2a squared right here. One's positive, one's negative. So those two are going to be what? Gone. What about this? 2 minus 2. Gone. And what are we left with? 4ah plus 2h squared over h. Which is excellent for us because what can we do at the top? Take an h out. So if we take an h out and we cancel it with the h on the bottom, we're going to be left with 4a plus 2h. So at this point, our answer, remember though, still have a limit. Our limit as h approaches 0 of 4a plus 2h. Okay, but now we can answer that question because we can directly evaluate this limit. Okay, so what is the limit as h approaches 0 of 4a plus 2h? 4a. Now, this expression right here is very powerful because this expression now is going to give us the slope of this curve, not any curve, just this curve, 2x squared plus 2. It's the slope of this curve at any point. And to double check, if we plug a 4 in there, like the previous one we did, what do we get? 16. And so again, why is it doing it in general more convenient? Because now this formula that we just figured out, this 4a, this is a formula essentially, isn't it? It's a formula for the slope of this curve at any point. So if I want to know the slope at 5 now, I wouldn't have to go through that whole process. I could just put it in there and say, oh, it's 20. Fair enough? All right. So again, we can do this for any function that we come across. Okay? So any function, whether it's a polynomial or otherwise. Okay, now the difficulty though is that the algebra for a polynomial, and if you think that that's tedious, okay, then you haven't seen some other functions, because a polynomial, the work for a polynomial is very easy compared to some functions. Okay, here's some good news. Okay, is again we can use this method to find that slope formula, if you will. We're going to give it a special name next week. Okay, but this slope formula that we just found here, we can use that method for any function, which is nice. Okay, now. Whether we can set it up and actually do the algebra for any function is another story. Okay? There's functions that we will not be able to do the algebra for, and the good news is that there's another method besides this that we can use to find the slope formula for other functions. Okay? So this method works very nice for polynomials and some other functions, but for some functions it's very difficult to apply. Okay? But luckily mathematicians before us have come up with better ways to do other functions than this. Okay? But one of the reasons why we learn it this way is because it's imperative to understand that what we found here is a slope. Okay? So the mechanics of this, I mean this part right here, this isn't calculus at all, this is algebra. Okay? But the calculus part of this is making sure we understand that this expression right here is going to give us a formula for the slope of any curve at any point. Okay? And that's why we learned this first, because this is important. And again, at some point, is there going to be a quicker way to do all this? Yes. Okay, there is. Okay, but like I said, we do it this way first, really for two reasons. One, so that we make sure we understand why this is a slope formula when we get done, and also to practice algebra, because most of us need algebra practice. So it doesn't hurt to practice these techniques either. All right? Questions so far? All right. So the two other things I want to go over with you, and that's we already said that the equation gives us the slope of a tangent line. And if we have a tangent line to a curve, let's say it looks like this. The questions in our homework are going to essentially say things like, find the equation for the tangent line to this curve at this point. So if I expand that to find the equation for this particular line, okay, I might find the slope, and if I do all my work and I find out that the slope is, let's say, -5, let's say for argument's sake, and I know that this is the point 2, 8. Okay? So again, I'm just making up an example of what it might be like if we were asked to find the equation for this tangent line. Okay, then what are we going to do here? Well, we calculated the slope with our new definition that we've learned. Okay? At this point, we found an answer. The slope is -5, and this is the point that we're dealing with here. So if we want to find the equation for that tangent line, okay, we're going to always, in this class, write the equation in point-slope form, which I'm going to write as y minus y1 m times x minus x1. Okay? So the point-slope form, we're going to essentially just fill in the blanks. And really, as soon as you see in any problem, write the equation for a line, you can write down the point-slope form immediately. Okay? And then know that we just have to find two things, a point and a slope. So if we put those in, as such, okay, that right there would be the answer. This would be the equation for our tangent line in this problem. Okay? Now, is there any good reason that I need to put that into slope-intercept form or standard form? No, not unless it says so. And the only reason that we would ever change that, okay, is if it tells you to put it in a different form, or if it is multiple choice and all the choices are in slope-intercept form. Okay? Then you'd have to do it. But like I said, from here on out, if it asks for an equation for a line, put it in point slope form and leave it alone. Okay? Because if you did this on the AP test and you did all the calculus right, and you wrote this down, and then you put it in slope intercept form and you made a mistake and your final answer had the wrong y-intercept, then guess what? Wrong. Right? So, lose point. You got 9 points in every problem. You lose a point, now you're down to 8 out of 9, 88%. Still good, but it's not 100. Right? So there's no good reason to put that in any other different form. Okay, I say that every year, but on the first quiz, guess what? People still put it in their other form. Why? Even if you get it right, what's the point? Why put it in a different form? And there's no reason to put it in a different form unless it says so. So just get in the habit at this point of leaving it in that form. Okay. Speaking of which, I'll say this now. If I have, let's say, 17x squared over 5x squared, and I want to know what the limit is as x approaches infinity, the answer here is 17 over 5. It's not 3.4. Okay? So get out of the habit of taking your calculator out and dividing 17 by 5 in this situation. There's no good reason to report the answer as a decimal. Okay? So do not do that from here on out. Okay? There's no decimals in this problem. Why would we give a decimal answer? Okay? The only thing you're getting yourself into is if you do that every time. Okay, if I had 17 divided by 6, okay, it wouldn't be 3.4. It would be 3 point something that had to be rounded. Okay? And then you'd have to give an approximate answer. So get out of the habit of changing things to decimals. There's no reason to have a decimal in this problem. Okay? So just another fact for this class that will always be our couple rules that we follow. Okay? So no need to change this to a decimal. Don't give me this answer as 3.4 from here on out. Okay? It's not 3.4, it's 17 fifths. Okay? 3.4 is the same in this case, but there's no good reason to change it to a decimal. So the less you do with your calculator, the better. Fair enough? So try to use it as little as possible. Because in this class and on the AP test, we have non-calculator tests. Okay? So you need to get in the habit of being able to do stuff without it. And no good reason to ever put that into your calculator unless it tells you to round it to the nearest tenth or something. Okay? So that's beside the point. But regardless, looking back, what you find in your book on page 87? Alright, we're going to revisit that the speed problem about the rock, if you will, from our section 2.1. And when we dealt with that, we were dealing with feet per second, so our equation was 16t squared. And we were asked to figure out what the instantaneous speed was at a given point. Okay? And with this as our equation, we know that that instantaneous speed is going to be the slope at that one instant, which we now know we can use our same definition, the limit as h approaches 0 of f of a plus h minus f of a over h. Now, one thing that people generally ask at this point, this a is actually an x coordinate, isn't it? Would there be any reason why I couldn't just use x here and have my answer, like my previous answer was 4a? Could it just be 4x and have my formula be in terms of x? Sure. It's just a variable. It doesn't really matter what letter you use here. The book generally uses a for the time being, but it really doesn't matter whether we use x or a. It represents an x value. It is what it is. So let's do the math on this one, and we already know how to do it with numbers. Well, a couple of us do. But when we do it with not numbers, if you will, it would be 16a plus h squared minus 16a squared all over h. So let's do this one in general. So at this point, when we get done, we're going to have an equation that's going to give us the instantaneous speed at any time. True? Yeah. Because we're going to do it in general. So therefore, we can just use our little formula that we're about to create, and we can find it at any time. So if I do 16 a squared plus 2ah plus h squared minus 16a squared all over h. And if we distribute, okay, and if you, at this point, I've written down like every step we've done here. If at this point you can see that when you multiply 16a squared and you're going to get negative 16a squared, it's going to be gone. Can we just go right to the next line and write 32ah plus 16h squared over h? I can, because I've done it enough. Okay. If you can't, do it every step and write them all down. But if you can visualize that a squared is going to be gone because of that, then go ahead and just do it and go to the next step. Okay. The other thing we can also do is instead of writing down, factor out h and cross the h out, Okay, we know that these h's are going to cross out, so we can just write 32a plus 16h. Okay. And with that, what's the limit as h approaches 0? Yeah, it's 32a. Alright, and so at this point, okay, when we're in free fall near the Earth's surface, we now have an equation that would give us the instantaneous speed of the object at any time. So if I'm up on a cliff and I drop this object, I could tell right now at 5 seconds the answer is going to be 160 feet per second. 32 times 5. True? And I don't have to do it all over again with 5 because I know the answer in general, don't I? Okay, now I can just plug 5 into the formula that I created. Okay? Now, the difficult part though is that every function that we have is going to have a different formula, isn't it? The previous one we had the formula was 4a. This one is 32a. True? So each function is going to have its own formula. Fair enough. Now, like I said, our work today is going to be essentially just doing some investigating with finding slopes of different curves. Okay. We are going to look at one last thing. I want you to find on page 88. The question that we're asked here in the 15 through 18 group. Say we look at number 16, for instance. We have negative x, and then we have x squared minus x. And this is for x less than 0, x greater than or equal to 0. Okay. And what the question is determine whether the curve has a tangent at the indicated point. If it does, give its slope. If not, explain why not. Okay, here's the deal on finding a tangent at a particular point. Here's what we can't have happen. If we have a nice smooth curve like all the ones we've dealt with so far, there's going to be a tangent line at every point. But if we have, say, a curve that looked like this, and then went off like this, for instance, okay, at that point A right there, if we want to draw a line that would touch this curve at exactly one point, okay, think about, I could draw, that point would be a tangent, wouldn't it? Or that line would be a tangent. Okay, couldn't I also draw one, though, that looked like that just touched the curve at that one point? And really, how many could I draw here? An infinite amount. Okay, we're going to put a name on that kind of point later. But bottom line here is that what the problem at this point is the following. Okay, as we approach A from the left, okay, we certainly have a limit here. Okay, the y values are the same on both left and right, true? But what's different is on the left side, the slope is what? Slope is negative something, isn't it? Okay, and on the right, as we come from the right, the slope is what? Positive. Those two slopes are not the same, are they? Okay, and if they're not, okay, then there's no slope at that particular point. Okay? There is no tangent at that point. Okay? So the issue that we're asking for here on a piecewise function like this is, okay, is there a tangent at the point x equals 0 for this one? Okay, well, if there was, then what would have to be the case? The slope on the left and the slope from the right would have to be what at that point? They have to be the same. They have to be equal. Okay? So let's calculate it and see if they are. So in practice then, I'm going to take, for my first function, I'm going to consider f of x to be negative x. And then f of a plus h minus f of a all over h. And again, we can put 0 in for h or for a if we want to for this particular problem. Okay? And it would make our work simpler if we did that. Okay? Because remember, it's x equals 0 that we're interested in. We don't have to write a formula this time. We can just find the answer. Okay? So let's just do it that way. So we would go f of h minus f of 0 all over h. Keep minus f of h because a is 0 here in our problem. And so if we do the work, we're going to put h into our function. That's going to be negative h minus 0 all over h. And when we do the work, we're going to negative h over h, which equals negative 1. And if we take the limit as h approaches 0 of negative 1, we get what? We get negative 1. It's a constant. Okay? Now, let's think about why that makes common sense in this problem. What function is it? Negative x. What's that look like? Looks like a line. What's the slope of that line? Negative 1. Where on that line would the slope ever not be negative 1? Nowhere. It's always negative 1. What do we just get for our slope? Negative 1. Shouldn't be surprising, should it? As a matter of fact, if we know that we're looking for the slope, did we really even need to do that with a linear function? No. We should have known it was negative 1. We didn't even need to bother with that, did we? Okay. Now, with a parabola, though, the slope is always different, depending on what point we're at. So now we would have to do that with a parabola. So just for time's sake, I'm going to just tell you what the answer is at this point. Okay. And the answer here, the slope indicator is 2a minus 1. Okay, so had we done all the work, this would have been our formula that we found. Okay, and if we put our formula in there, or put our 0 in there, if you will, the x value in question, our answer is -1. So in this particular case, what do we see? That both on the left and right side of 0, both functions give us the same slope of -1. So the answer to this question then would be yes. Okay, there would be a tangent at that point. And think about how that might look in practice. If we had the slope is -1, let's say it looks something like this coming off the parabola. Right? If it comes off the parabola and the slope is -1 right here, and it goes straight into a line that has a slope of -1, the slope on the left and the slope on the right would both be -1. So that means there would be a tangent at that point. Okay? Now, what would be a no in this case? Had we gotten -1 and 0 or something different than -1? Okay, so if we had done both sides and gotten something different, then we would have said no, there's no tangent there. Fair enough? So again, in order to be a tangent at a point, okay, we have to have the slope on the left and the slope on the right have to be equal to each other. Okay? What if we were given a function that looked like this? And they want to know, is there a tangent at this point? I mean, it's not even continuous at that point, so could there be a tangent there? No. Okay. So, well, that's actually one of the properties that we'll study next week, that, you know, ultimately, if there's no continuity, then there wouldn't even be any, we wouldn't even ask the question about what's the slope there. Okay? Okay, so with that said, we're going to try some problems here for Monday.